Thousands of ducks are released straight into rice paddies in the middle of the growing season. No fences, no supervision, just ducks, rice, and what looks like total chaos. At first glance, it feels like a disaster waiting to happen. Rice fields are fragile. The ecosystem is sensitive. One wrong move could wipe out an entire harvest. Yet this is the method China chose to rescue more than 40% of its farmland, severely degraded by the pressure of 4 million tons of pesticides used every year, and something no one expected happened. After just one growing season, the rice fields didn't collapse. They began to recover. So what was really happening beneath the water's surface? And why is a method that seems ancient now challenging modern industrial agriculture? Mandarin Tech reveals the story in this video. In less than a century, farmland across the world has become almost completely mechanized. Transplanters, harvesters, and sprayers replace manual labor. Synthetic fertilizers made crops grow faster. Pesticides allowed pests and diseases to be controlled at a scale never seen before. As a result, global food production increased many times over, but the cost has become increasingly clear. Each year, agriculture is responsible for about 20–25% of total global greenhouse gas emissions, most of it coming from chemical fertilizers and degraded farmland. Pesticides alone have severely reduced soil microorganisms, disrupting the biological cycles that naturally maintain soil fertility. According to many studies, more than 40% of the world's agricultural land is gradually losing its ability to regenerate, forcing farmers to apply higher and higher amounts of fertilizer and chemicals just to maintain the same yields. The problem becomes even more serious when more than half of the world's population depends on rice. Rice fields are not just a farming system. They are a foundation of global food security. When this ecosystem weakens, the risk no longer stays within individual fields, but spreads across the entire system that feeds billions of people. A dangerous cycle begins to form, quietly weakening agricultural ecosystems season after season. If modern agriculture is creating its own problems, then where does the real way out lie? Ironically, the answer to the modern agricultural crisis lies in practices that existed long before chemicals ever appeared. For centuries in rice-growing regions across East Asia, rice fields were never treated as a single-purpose production surface. They were living ecosystems where rice and ducks coexisted. Ducks were released into the paddies shortly after transplanting, moving all day through the shallow water, eating insects, young weeds, and gently stirring the top layer of mud. Their droppings became a direct source of nutrients for the soil, replacing much of the need for external fertilizers. No machinery, no pesticides, yet the system maintained stable yields over long periods of time. Agricultural records show that the rice duck model has been practiced for more than 600 years, long enough to prove that its effectiveness comes not from sheer output, but from biological balance. Within this system, pest outbreaks were rare, the soil was not exhausted, and rice fields were able to sustain themselves season after season. When the first ducks are released into the rice fields, the natural reaction for many people is concern. The rice plants are still young and fragile, and just one strong impact could ruin an entire harvest. But very quickly, a different pattern begins to emerge. Ducks largely avoid the rice plants. Instead, they focus on whatever moves in the water and grows faster than rice. Exactly the things farmers constantly struggle to control. Brown plant hoppers, stem borers, leaf hoppers, and various aquatic insects become their main food source. As the flock moves continuously through the field, the ducks disrupt the pest life cycle at an early stage, causing pest populations to drop noticeably within just a few weeks. At the same time, their movement stirs the water surface, destroying mosquito larvae and other harmful organisms, significantly reducing the need for pesticide spraying. Weeds also lose their chance to grow as they once did. Ducks feed on young weed shoots, duckweed, barnyard grass, and even wild rice, plants that normally compete directly with rice for nutrients. Every step the ducks take interrupts weed root formation, preventing weeds from developing into dense mats. This constant disturbance creates an unexpected effect. Oxygen is introduced into the water and the top layer of soil, reducing anaerobic conditions, limiting soil compaction, and allowing rice roots to grow deeper and stronger. Many researchers compare this to a form of natural tilling that happens throughout the day. And throughout this entire process, duck droppings are spread evenly across the field like a continuous stream of organic fertilizer. Rich in nitrogen and organic matter, this nutrient source feeds both the soil and the rice plants more steadily, avoiding the over-application common with chemical fertilizers, while also reducing the risk of surface and groundwater pollution. To turn what seems like chaotic movement into an advantage, farmers must control every step of releasing the ducks with precision. The ducks are introduced only 2 to 3 weeks after transplanting, when the rice plants are strong enough to withstand movement in the water without bending or breaking. If released earlier, young seedlings can be damaged. If released too late, the effectiveness of pest and weed control drops significantly. Duck density is also not something that can be left to chance. Studies in China and Japan show that the optimal range is typically 150 to 300 ducks per hectare, depending on soil conditions, water depth, and rice variety. Too few ducks produce a biological impact that is too weak to replace chemical inputs. Too many, on the other hand, can cloud the water, stress the root system, and reduce the plant's ability to photosynthesize. Equally important is the timing of removing the ducks from the field. When rice enters the panicle initiation stage and begins preparing to flower, the ducks must be completely withdrawn. This is the most sensitive phase of the rice plant, where even a small disturbance can directly affect the number of grains formed on each panicle. In rice duck farming systems monitored in China and Japan, spending on pesticides typically drops by 50 to 70%, while chemical fertilizer costs fall by 20 to 40%. This means total input costs per hectare of rice fields are significantly reduced, often starting in the very first growing season. For many small farming households, this is a matter of survival at a time when agricultural input prices continue to rise. But the benefits do not stop at simply spending less. The value of the rice itself also changes. Rice produced in rice duck systems is often classified as ecological rice or low-chemical rice. And in many Asian markets, it can sell for 10 to 30% higher prices than conventionally grown rice. Consumers are willing to pay extra for safety and sustainability they can recognize and trust. Alongside rice, the duck flock becomes a real economic product of its own. With access to natural food sources in the fields, ducks grow quickly with low reliance on commercial feed and minimal dependence on antibiotics. At the end of the season, farmers can sell duck meat or eggs, creating an additional income stream independent of rice prices and helping to spread market risk. In many systems, revenue from ducks is enough to offset a large share of rice production costs, turning an ecological system into an economic model capable of balancing itself. As chemicals are withdrawn, rice fields begin to change in ways people have long forgotten. The water gradually becomes clearer, algae levels drop, and the smell of anaerobic decay disappears. Creatures that were once pushed out of the farming system start to return. Beneficial insects appear first, followed by frogs, small fish, dragonflies, and water birds. The rice field no longer operates like a starch factory, but slowly reclaims its role as a living ecosystem. More importantly, studies have recorded a 20 to 30% reduction in methane emissions compared to conventionally farmed, chemical-intensive rice fields. The constant movement of the ducks disrupts anaerobic conditions in the soil, the primary factor behind methane production in flooded rice paddies. This means rice fields not only reduce their environmental impact, but actively contribute to mitigating climate change. At a deeper level, the rice duck model is not simply less harmful agriculture. It is moving toward regenerative agriculture, where soil is restored, biological cycles are reconnected, and ecosystems can sustain themselves over multiple growing seasons, rather than constantly needing to be rescued by chemical inputs. This system requires precise farming knowledge, from the timing of duck release and flock density, to water level management and close monitoring of rice growth. Even small mistakes can quickly turn biological benefits into production risks. There are also threats from predators. Snakes, foxes, feral dogs, and birds of prey can cause serious losses if the ducks are not properly protected. In regions with labor shortages or limited capacity for supervision, this risk becomes a real barrier. More importantly, not every ecosystem is suitable. Areas without a stable water supply, fields with steep terrain, or rice paddies that have been heavily polluted may not provide the biological foundation the system depends on. This shows that the rice duck model is not a universal formula, but a solution that must be carefully chosen, adapted, and applied in the right place, under the right conditions. When the idea of using rabbits to revive the desert first began to take shape, Wong understood one thing clearly. For the rabbits to survive, he first needed a plant strong enough to stand its ground against scorching winds and shifting sand. Out of dozens of options, only one species met every harsh requirement: the willow. Willows became the foundation of the entire ecosystem because their roots can reach nearly 90 meters deep, tapping into water layers that most plants can't reach. Once those roots take hold, they stabilize the sand, weaken the force of the wind, and create a cooler microclimate stable enough for life to begin. That's why the willow wasn't just another plant. It was the starting switch for the entire ecological loop. To turn willows into the backbone of the ecosystem, Wong had to face a challenge that had gone unsolved for centuries. How do you keep a tree alive in a place where the ground gets hot enough to scorch insects in minutes? In Kubuchi, the wind doesn't just blow, it carries sand like razor blades, capable of stripping bark and ripping out roots in just a few days. On top of that, surface temperatures above 70 degrees Celsius make germination almost impossible. That's why planting a willow here isn't as simple as dig a hole and drop in a tree. It's a constant battle with nature. Planting teams have to track faint pockets of moisture hidden beneath the sand, the last lifelines of the land. When they find a spot that can hold water, they dig deep pits and immediately shield them with wire mesh, reeds, and temporary barriers to protect them from the next strong gust of wind. The young willows are treated with special moisture-retaining solutions and anchored with wooden frames so they won't be ripped out overnight. Water has to be used sparingly. Drip irrigation delivers only enough for the roots to sense life and push themselves deeper into the soil, clinging to the earth, clinging to their only chance of survival in this harsh sea of sand. Once the first bands of willow trees grew large enough to cast shade and retain moisture in the soil, Wong introduced the most important link in his restoration model, bringing Rex rabbits into a closed, controlled ecosystem. These rabbits were never released into the wild. They were raised in tightly managed ecological farms where each one had both economic and ecological value. Their meat became a clean food source, their fur was used in high-end fashion products, and their organs supported traditional medicine. But what truly turned the Rex rabbit into an ecological weapon was its droppings. Rabbit manure is extremely rich in nitrogen, phosphorus, and potassium, nutrients the desert lacks entirely. When released into the environment, it doesn't just fertilize the soil, it helps loose sand bind together into a moist, nutrient-rich layer of humus. Even more interesting, Rex rabbits cannot digest grass seeds, so every time they dig or forage, intact seeds end up mixed in their droppings and get scattered across the land, each one wrapped in a natural fertilizer pouch that allows it to sprout even under brutal desert conditions. As a result, new vegetation keeps appearing on its own, expanding the green coverage with minimal human intervention. Thanks to the arrival of the Rex rabbits, the structure of the new ecosystem gradually became clear and began operating like a self-balancing machine. The willow canopies provided shade and a steady source of food for the rabbits. The rabbits, in return, gave the land what it lacked most: nutrient-rich humus. This new soil held moisture, reduced erosion, and became the foundation for even stronger willow growth. This closed loop turned every hectare of sand into a natural humus-producing factory, generating more than 5 tons a year. Enough for a once barren, rock-hard stretch of desert to transform into fertile farmland in just 3 to 5 years. When the model scaled up, more than 200 million willow trees formed a massive green barrier, cutting wind speeds by up to 90% and preventing over 15 million tons of sand from shifting each year. Areas that were once helpless against sandstorms have now been restored with greenery across 700 to 800 square miles, creating a solid foundation for expanding the Rex rabbit farming model. As the ecosystem stabilized, the population of 1.2 million Rex rabbits not only helped regenerate the soil, but also became an economic spearhead, generating over 100 million yuan each year and providing thousands of families with a sustainable source of income in a place once considered uninhabitable. It sounds unbelievable, but Vietnam is now raising billions of golden apple snails in closed farming systems. A species once seen as a nightmare for agriculture is now being reproduced as a valuable resource. Few people realize that this creature can wipe out an entire rice field in just one night. With its explosive reproduction rate, golden apple snails spread like living waves, destroying young rice seedlings and pushing much of Southeast Asia into repeated crop failures. Countries tried everything, spraying chemicals, mobilizing thousands of people to collect them by hand, and spending millions of dollars on large-scale control campaigns. But the more they tried to eliminate them, the faster the snails returned, making control efforts almost meaningless. It became an invasive species that was nearly impossible to remove. So why, when the entire region struggled to stop them, did Vietnam choose to farm them instead? Is this a brilliant strategy or a risky gamble? Let's find out with Mandarin Tech. Originally from South America, the golden apple snail became a global agricultural nightmare within just a few decades. Unlike typical pests, it reproduces at an almost uncontrollable rate. A single adult female can lay 300 to more than 1,000 eggs at a time, and within 2 to 3 weeks, a new generation is ready to reproduce again. Under favorable conditions, their population can grow to tens of millions in just one rainy season. In the United States, especially Florida and Texas, golden apple snails have disrupted wetland ecosystems, reduced native aquatic vegetation, and forced environmental agencies to spend over $2 to $3 million each year on monitoring and control. But the most serious damage has occurred in Southeast Asia, where rice farming plays a critical role. What makes them especially destructive is how they attack. They don't eat mature leaves or fully developed plants. Instead, they target young rice seedlings, the most vulnerable stage of the crop. Once damaged at this stage, the plants cannot recover. Since being recorded in 1980, golden apple snails have destroyed more than 50,000 hectares of rice fields in the Philippines. In Thailand and Indonesia, rice yields in many areas drop 10% to 40% per year, forcing farmers to replant multiple times in a single season. The impact spread beyond Southeast Asia. In Japan, China, and South Korea, farmers reported rice fields transplanted in the afternoon, turning into empty flooded plots just hours later. In southern China, damage during major outbreaks was estimated at over $1 billion per year. The moment bright pink egg clusters begin appearing along the edges of rice fields, many farmers know the battle with golden apple snails has started again. In many rice-growing regions, control measures are deployed almost immediately. Drones take off at dawn, spraying chemicals across fields covering hundreds of square kilometers, hoping to stop the invasion before it spreads to nearby areas. Countries have spent hundreds of millions of dollars on pesticides and large-scale control campaigns. In many places, farmers still go into the fields before sunrise, walking through cold mud to collect snails by hand and destroy egg clusters before they hatch into a new generation. In the Philippines, some farmers start at 4 a.m., yet by midday the fields can still be covered with snails, as if nothing had been removed. But the problem has never been a lack of effort. It lies in the way this species survives. Golden apple snails do not appear once and disappear. When one field is cleared, new eggs have already hatched somewhere else. When one area finally brings the outbreak under control, another population returns after the next rain. Over decades, the fight against golden apple snails has slowly become a familiar repeating cycle. And as this cycle continues, the cost is not only measured in lost rice production, it is also seen in fields becoming increasingly dependent on chemicals, and in agricultural ecosystems gradually losing the natural balance they once had. As one of the world's largest rice exporters, Vietnam could not stay out of this battle. By the late 1980s, when golden apple snails began spreading across the Mekong Delta, the region producing more than half of the country's rice, many provinces reported losses of 20 to 30 million US dollars per year. During peak outbreak years, farmers often had to replant 2 to 3 times in a single season, not because of drought or floods, but because a small species was reproducing faster than people could control. In many farming areas, a natural solution was introduced, releasing ducks into the fields. Hundreds, sometimes thousands of ducks were guided across newly planted paddies to eat young snails and their eggs. In suitable areas, this method helped significantly reduce snail populations without additional chemicals, but its effectiveness did not last on a large scale. Not every field could support duck grazing. Not every region could maintain flocks large enough to control outbreaks. And after each rainy season returned, the bright pink egg clusters kept appearing along the field edges. After decades of fighting a species that seemed impossible to eliminate from rice ecosystems, a bold idea began to emerge. What if the enemy of rice fields could actually become a resource to feed people instead? Taking action quickly, in several northern delta provinces such as Tai Binh, Nam Dinh, and Hung Yen, closed-system golden apple snail farms were rapidly established, turning a species once targeted for elimination into a livestock resource managed under a clearly controlled process. Inside these farming areas, rows of concrete tanks are arranged side by side, supported by aeration systems operating almost continuously. Water temperature is maintained between 25 and 30 degrees Celsius, allowing the snails to grow steadily nearly year-round instead of depending entirely on the natural rainy season. On the water surface, a thin layer of floating plants is added to provide shade, supply natural food, and help stabilize the environment for young snails during their early growth stage. Each tank can maintain densities of 10,000 to 30,000 individuals, making production efficiency far higher than under traditional field conditions. After only 2 to 4 months, a batch can already reach harvest size, much faster than most familiar livestock in traditional agricultural systems. While freshwater fish and poultry farming still depend heavily on land area and stable seasonal feed supplies, golden apple snails can feed directly on duckweed, leafy greens, and agricultural byproducts as their main food source. With high stocking density, low production costs, and a short growth cycle, these farms are beginning to operate like continuous biological food production systems, transforming a species once considered a pest into a new rural livelihood resource. No longer are the bright pink egg clusters crushed along the edges of rice fields the moment they appear, as they once were. Inside closed farming systems, they are now carefully collected and transferred to separate incubation areas, where temperature and humidity are kept stable to protect each new generation even before hatching. After just 10 to 15 days, the eggs begin to split open and hatch into young snails. Thanks to continuously controlled conditions, their survival rate becomes significantly higher than in the wild, where most eggs are usually washed away by rain or destroyed early in their development. For the first time, egg clusters that once signaled the start of a new outbreak are no longer treated as a warning sign. Instead, they have become the starting point of a controlled production cycle that farmers can maintain throughout the year. After several weeks of being raised in closed tank systems, the moment of harvesting golden apple snails finally arrives. There is no longer a need to bend over in muddy rice fields to collect them, one by one, as before. Farmers simply drain the tanks, gather the snails into one corner, and harvest them in large batches. Thousands of snails quickly cluster into dense layers at the bottom and are lifted out with mesh baskets in a process that can be repeated almost every day. In just a few hours, a small farm can collect 30 to 50 kilograms of market-ready snails, sold at around 2.5 to 3 US dollars per kilogram, an amount that previously could take an entire day in the fields and still not be enough. Immediately after harvesting, the snails are moved to a central cleaning area. Here, each batch is poured onto long washing tables with continuously flowing water to remove mud from the shells. Workers stand along both sides of the sorting tables, mixing the snails by hand and removing impurities in undersized individuals. Large plastic baskets are constantly replaced in a steady collection rhythm. After several hours of washing and soaking, the snails are ready for transport, sale, or further processing. Fresh batches of golden apple snails are quickly moved to a cleaning area after harvesting, where they are soaked in water for several hours to remove mud and remaining impurities from their shells. This is an important preparation step that helps make the snail meat clearer, firmer, and naturally sweeter before moving on to further processing. One of the simplest and most popular dishes is boiled snails with lemongrass and ginger. Fresh snails are dropped into pots of steaming boiling water, releasing a light, spicy aroma. In many northern neighborhoods of Vietnam, a hot plate of boiled snails usually costs about $2 to $3, often served with a strong ginger chili dipping sauce. It has become a familiar afternoon snack in urban street food culture. A richer option is stir-fried snails with chili. After cleaning, the snails are quickly cooked over high heat with golden fried garlic and fresh sliced chili. As the fish sauce thickens around the shells, the spicy fragrance spreads rapidly, creating a dish that is both crispy and full of flavor, making it hard for diners to stop after the first bite. In many night markets, snails are also skewered and then steamed with lemongrass or grilled over charcoal. Rows of shiny golden snails cook over hot stoves, releasing a distinctive rich aroma. Within just a few minutes, they become a popular street food. Clear evidence that a species once known for damaging rice fields has now become a familiar local delicacy on everyday dining tables. But the value of golden apple snails does not stop at the dining table. A large portion of the harvest actually moves in another direction, into the livestock and aquaculture industry. After being crushed or ground, golden apple snails become a natural high-protein feed source for farmed fish, such as grass carp, tilapia, and snakehead fish. With a protein content of about 12 to 16%, snail meat helps fish grow faster during their early development stages and significantly reduces dependence on industrial fish meal, one of the most expensive ingredients in aquaculture today. In many fish farming models in the Mekong Delta, using locally available snails can reduce feed costs by 10 to 20% per production cycle. Golden apple snails are also widely used in poultry farming, especially for free-range chickens. When chopped or mixed directly into feed, the meat provides an easily digestible source of protein, while the calcium-rich shells help support bone development and improve egg quality. As a result, large commercial fish farms and poultry operations are beginning to form direct supply connections with snail farming facilities. These links are gradually creating a more integrated production chain where golden apple snails can be collected, processed, and reused efficiently within local farming systems. In this way, a species once considered a destructive agricultural pest is now becoming a new and valuable component of modern livestock production. For decades, golden apple snails were seen only as a species that needed to be controlled. But as more commercial farming models began to appear, a larger question started to emerge. What would happen if this biological resource were used on an industrial scale? Each year across Southeast Asia alone, millions of hectares of rice fields report the presence of golden apple snails. This means a massive amount of natural biomass already exists within agricultural systems, yet most of it still remains underused. At the same time, the global livestock and aquaculture industries are becoming increasingly dependent on imported fish meal and expensive industrial protein sources. As a result, developing locally available alternative feed materials is becoming a clear and growing trend. With their fast reproduction rate and short life cycle, golden apple snails are now being considered a promising raw material for future biological feed production systems. Several pilot models in Vietnam and China have already shown that collecting and farming snails under controlled conditions can create a stable year-round supply instead of relying entirely on natural populations as before. When organized into a coordinated production chain, a species once known for causing serious crop losses could become part of a circular agricultural system, where what once damaged rice fields can return to support agricultural production itself. In this way, golden apple snails are gradually being redefined, not only as a pest to control, but as a resource with long-term potential in modern agricultural systems. This new approach is not limited to golden apple snails. It reflects a broader shift in modern agricultural thinking worldwide. For many years, invasive species were almost always seen as threats that needed to be eliminated as quickly as possible. But as control costs continue to rise and effectiveness declines, more countries are exploring a different strategy, turning these pests into usable resources. From crop-damaging insects raised as livestock feed, to invasive seaweed harvested for biological fertilizers, new economic models are emerging based on the same idea. Rather than fighting nature, people are learning to work with what already exists in the ecosystem. In that context, the story of golden apple snails is no longer just a local solution used by farmers in a few Asian countries. It is becoming a clear example of a new direction for 21st century agriculture, where species once seen as problems can become part of the solution. After thousands of years shaped by colonial history, many parts of Africa were left with outdated infrastructure. Into this landscape, China introduced a new wave of development in Kenya, bringing advanced technology and modern engineering to build a massive railway system. Elevated tracks now stretch across open savannas, kilometer-long viaducts cross difficult terrain, and modern operating technology, never before seen on such a scale in Africa, became part of the project. Tens of thousands of workers, heavy machinery, and billions of dollars in investment were mobilized to complete the standard gauge railway in just a few years, an ambitious project widely seen as capable of reshaping Kenya's economic future. So how did China build this railway? Why was it willing to invest so heavily in Africa? And what truly lies behind this mega infrastructure project? Let's explore with Mandarin Tech. Before China's involvement, Kenya's railway system was largely a legacy of British colonial rule. The infrastructure had deteriorated over decades, trains operated slowly, and transportation costs from the port of Mombasa into inland East Africa ranked among the highest in the world. Seeing this massive infrastructure gap, China proposed building a modern railway network as part of the Belt and Road Initiative, turning Africa's development needs into a strategic opportunity for itself. In 2014, construction of the standard gauge railway began with a loan of about $3.8 billion from the China Exim Bank. The state-owned China Road and Bridge Corporation was responsible for design, construction, and technology deployment. In less than 3 years, the 480-kilometer Mombasa to Nairobi Railway officially opened in 2017, complete with Chinese locomotives, signaling systems, technical standards, and workforce training programs, transferred alongside the infrastructure. Despite investing billions of dollars, China's interest was not focused on short-term profit, but on long-term strategy. The loans generate financial returns over decades. Chinese companies gain overseas projects while exporting steel, machinery, and railway technology. In other words, China was not simply building a railway, it was building economic influence, supply chains, and geopolitical presence in one of the fastest-growing regions of the world. First, China's top engineers developed the overall concept for the railway and began conducting on-site terrain surveys. Engineers and planning experts carefully analyzed Kenya's landscape to understand the challenges of the route. Using satellite data, aerial survey aircraft, and modern measuring equipment, they identified the most efficient path to reduce construction costs while minimizing environmental impact. In the end, they finalized a railway line stretching 472 kilometers, running from the port of Mombasa to the capital city of Nairobi. Most sections of the line were built as elevated railway structures, ensuring stable foundations and allowing trains to operate safely and continuously across different types of terrain. After the route had been defined, The next challenge was to reshape the terrain along the entire construction corridor. In Kenya's sandy and uneven landscapes, hundreds of bulldozers and grading machines were deployed to cut down high mounds while filling in lower areas. The goal of this stage was to create a stable and balanced surface, strong enough to support heavy construction equipment and the future railway system. Each section of ground was carefully scraped, leveled, and inspected under the supervision of engineering and surveying teams. Specialists continuously measured elevation and slope to ensure the line maintained the required accuracy across dozens of kilometers of natural terrain. Excess soil and sand were transported away from the construction zone by conveyor systems and heavy trucks. This process created a flat construction site, ready for the compaction step. After the bulldozers finished leveling the ground along the railway corridor, the sandy soil still needed further stabilization before construction could continue. Engineers realized that adding controlled moisture to the loose soil would help the sand particles bind together more tightly, forming a denser and more stable base. Using water pipelines and long spraying arms, groundwater was evenly sprayed across the construction site, it allowing moisture to gradually penetrate into the layers of soil below. Once the moisture reached the proper level, engineers used a technique called dynamic compaction, where a steel weight weighing tens of tons is suspended from a crane and repeatedly dropped onto the ground. Each impact creates a powerful compressive force that helps the layers of sand and soil below become tightly compacted, forming a more stable foundation. Immediately after that process, heavy rollers began moving back and forth across the surface, compacting the ground to remove air pockets and lock the sand particles together. The deep rumble of the steel drums echoed across the construction area as each pass of the rollers transformed the soft soil into a flat and uniform foundation. By the time the surface dried again under the sunlight, the ground had hardened enough to support the weight of cranes, concrete mixers, and heavy material trucks. After the ground surface had been fully compacted, construction crews began spreading a base layer of soil over the stabilized sand along the railway corridor. Dump trucks continuously unloaded loads of the region's characteristic red soil from Kenya, which bulldozers then pushed and leveled across the construction site. This layer added additional weight to the sand beneath. It was evenly spread and repeatedly compacted with heavy rollers, forming a dense and solid base layer. Once completed, the surface was strong enough to support the weight of concrete beams and columns, weighing up to 40 to 60 tons, which would later be installed along the viaducts and elevated railway sections of the line. On the reinforced and compacted ground, the railway bridge piers gradually began rising along the corridor of the line. These massive concrete columns were positioned about 35 meters apart, with each pier reaching up to 15 meters in height and weighing nearly 90 tons, depending on the terrain and structural load requirements. Across the entire railway route, thousands of concrete piers were constructed, forming long, straight rows stretching across the plains of Kenya. Each pier was cast using slip-form molds and reinforced with high-strength steel to ensure durability against high temperatures, strong winds, and the constant vibrations generated by passing trains. The spacing between the piers was carefully standardized to improve the stability of the viaduct structure and reduce the effects of thermal expansion. From a distance, these endless lines of concrete pillars extended toward the horizon, forming a vast framework of steel and concrete, the structural backbone of a modern railway gradually taking shape across the vast landscapes of East Africa. The next stage involved manufacturing precast concrete box girders, the structural elements that would connect the piers and form the bridge deck for the railway. Inside fabrication yards located near the construction site, steel molds measuring about 30 to 32 meters in length were precisely assembled to cast each girder. Within these molds, old reinforced steel cages and pre-stressing cable systems were carefully positioned before high-strength concrete was poured in and vibrated to remove trapped air bubbles. After the concrete hardened, each bridge girder, weighing between 70 and over 100 tons, was removed from the mold and transported to storage yards. Thousands of these massive girders were produced continuously, ready to be lifted and installed onto the bridge piers to form the elevated railway structure. Once the precast concrete girders were transported to the construction site, the installation of the bridge spans began. Heavy lifting cranes or a launching gantry, a specialized beam installing frame that moves along the bridge piers, were used to lift each concrete girder weighing dozens of tons to heights of several tens of meters. Each girder, measuring about 30 meters in length, was carefully positioned between two bridge piers with extremely high precision, and with tolerances measured in just a few millimeters. Once the girder was placed on the bridge bearings, engineers temporarily secured it before installing the pre-stressing cable system running through the body of the girder. High-strength steel tendons were then tensioned using hydraulic jacks, creating compressive forces that allowed the entire bridge span to behave like a single, continuous, and stable concrete structure. After the tensioning process was completed, a concrete grout or specialized mortar was injected into the cable ducts to protect the steel from corrosion. The next girder was then lifted and installed in the same way, each span gradually linking together like enormous structural chains. In just a few hours, a viaduct section stretching dozens of meters could be completed. As thousands of girders were assembled, the elevated railway slowly took shape, extending across the vast plains of Kenya. Next, the process moves to the rail manufacturing plant, the place where massive steel rails are produced before being transported to the construction site. Inside the facility, heavy steel billets or blooms, each weighing several tons, are stacked in long rows within the raw material storage area. Overhead cranes and automated conveyor systems gradually move these steel blocks toward a large industrial furnace, where temperatures can reach up to 1,200 degrees Celsius. At this stage, the intense heat softens the metal, preparing it for the next step of the process, rolling and shaping the rails. After leaving the furnace, the glowing steel billets move directly into the rolling mill, where the actual shaping of the railway rail begins. At this stage, the steel is still heated to around 1,000 to 1,100 degrees Celsius, making it soft enough to be stretched and formed under enormous pressure. The billets pass through a long series of rolling stands, each equipped with specially designed steel rollers that gradually squeeze and elongate the metal. With every pass through the rollers, the thick rectangular billet becomes longer and thinner, slowly transforming into the recognizable rail profile. The rollers are precisely machined to create the three key parts of a railway rail: the head, which supports the train wheels, the web, the vertical section that distributes the load, and the foot, the wide base that anchors the rail to the sleepers. During this rolling process, the steel can extend from an initial billet just a few meters long into a rail that measures up to 100 meters or more in length. Powerful motors control the speed of the rollers to ensure the metal flows evenly, while sensors continuously monitor temperature and alignment to prevent deformation. Sparks, heat waves, and the thunderous sound of machinery fill the rolling hall as each glowing steel beam is stretched into its final shape. By the time the rail exits the final rolling stand, it has already taken on its precise geometric profile, ready to move into the next stage of controlled cooling and straightening before being cut and prepared for railway installation. After the massive steel rails are manufactured, another critical component is still needed to ensure the stability of the entire railway system: concrete sleepers. These concrete blocks sit directly beneath the rails and are responsible for maintaining the correct spacing between the two rails while transferring the weight of passing trains down to the track foundation. In railway material factories, pre-stressed concrete sleepers are produced by pouring high-strength concrete into steel molds that are about 2.5 meters long. Before the concrete is poured, pre-stressing steel cables are tensioned inside the mold, allowing the hardened concrete to achieve greater load-bearing capacity and improve resistance to cracking. Once the concrete reaches the required strength, the sleepers are removed from the molds and fitted with elastic rail clips, steel base plates, shove-in fastening bolts, components that will firmly secure the rails above. Each sleeper typically weighs around 250 to 300 kilograms and is installed at intervals of about 60 centimeters, meaning that 1 kilometer of railway can require approximately 1,600 to 1,700 sleepers. Their main function is to distribute the weight of trains evenly onto the ballast layer and the subgrade below, while maintaining the precise distance between the two rails. This ensures that trains can operate smoothly, safely and reliably for decades of service. After the concrete sleepers are transported to the construction site, workers begin assembling the steel rails into complete track modules on an assembly platform. Long steel rails, often tens of meters in length, are carefully placed onto the steel base plates already attached to the sleepers. They are then secured using elastic rail clips and anchor bolts, which firmly lock the rails in position. Each assembly typically includes 20 to 25 sleepers, and are forming a completed rail section measuring about 12 to 15 meters in length. Once all the clips and bolts are tightened, the rail sleeper structure becomes a single rigid unit, strong enough to be lifted by cranes. These finished track modules are then lifted and placed directly onto the prepared ballast layer along the railway foundation. This modular installation method allows construction to proceed much faster and with greater precision compared to assembling each individual component directly on site. Once the rail modules have been fully assembled, they are transported to the construction area. At the site, heavy cranes or dedicated track lifting systems raise each rail sleeper section, typically 12 to 15 meters long, off the transport wagon. Workers then carefully guide and position the module so it can be placed precisely onto the prepared concrete bridge deck or track foundation. Each section is aligned with great care to ensure that the distance between the two rails always maintains the standard gauge of 1.435 meters. When two adjacent modules are positioned correctly, the ends of the steel rails are joined using thermite welding or specialized electric welding, creating a seamless connection that reduces vibration and improves the durability of the entire railway line. After the weld is inspected and ground smooth, the rail clips and bolts are tightened onto the sleepers to firmly secure the structure. Additional modules are then installed in the same way, one after another, gradually forming a continuous steel railway line that stretches along the route. What if I told you that something considered waste on livestock farms could be transformed into enough energy to heat thousands of homes? It may sound hard to believe, but that's exactly what's happening in Denmark, home to one of the world's largest biogas plants. Using gigantic artificial stomachs filled with trillions of microorganisms, organic waste is converted into renewable gas that can be fed directly into the national energy grid. So how does this remarkable process work? Let's find out with Mandarin Tech. Nature Energy Korsgro is part of Denmark's ambitious strategy to turn waste into energy. Instead of allowing millions of tons of livestock manure and organic byproducts to become an environmental burden, this Nordic nation has built massive biogas facilities that convert them into renewable gas capable of being injected directly into the national energy network. Located in western Denmark, Korsgro is one of the largest biogas plants in the world. Each year, the facility processes more than 1 million tons of biomass, producing tens of millions of cubic meters of biomethane. At the heart of the plant are 7 gigantic anaerobic digesters, each holding nearly 10,000 cubic meters of material. Operating around the clock, the entire system transforms enormous volumes of agricultural waste into a valuable source of renewable energy. To produce tens of millions of cubic meters of biomethane every year, Nature Energy Korsgro must first solve a challenge that sounds simple but is enormous in scale: how to transform more than 1 million tons of organic waste into fuel. Every day, waste from dairy farms, pig farms, food processing facilities, and many other organic sources arrives at the plant's central reception area. Over the course of a year, the total volume is equivalent to tens of thousands of heavy-duty truckloads. After being weighed, inspected, and cleared of contaminants, the material is shredded, mixed, and pumped into the massive digestion tanks located at the heart of the facility. Inside 7 anaerobic digesters, each with a capacity of nearly 10,000 cubic meters. The organic mixture is continuously stirred and maintained at a temperature of approximately 38 to 40 degrees Celsius. In many ways, each digester functions like a gigantic artificial stomach, operating at full capacity within an industrial complex, where trillions of microorganisms work around the clock. In this completely oxygen-free environment, bacteria begin breaking down the organic material and releasing biogas. The process does not take place over a few hours but continues for several weeks. Every remaining unit of energy within the waste is extracted as efficiently as possible, producing a gas mixture containing methane, carbon dioxide, and small amounts of other impurities. However, this gas is not sent directly into the gas network. Instead, it is transferred to a gas upgrading facility where carbon dioxide, water vapor, sulfur compounds, and other unwanted substances are removed through a series of treatment processes. After purification, what remains is high-quality biomethane with a methane concentration that can exceed 97%. From a practical standpoint, this renewable fuel is nearly indistinguishable from natural gas extracted from underground reservoirs. The biomethane is then compressed and injected directly into Denmark's national gas grid. As a result, energy that once existed in livestock manure, agricultural residues, and food waste can now be used to heat homes, power businesses, and support a wide range of activities across the country. But have you ever wondered what happens to these giant artificial stomachs after years of continuous operation? Although most of the organic material is broken down by microorganisms and converted into biomethane, not everything that enters the digester simply disappears. Over time, sand, gravel, plant fibers, contaminants, and other hard-to-digest materials gradually settle at the bottom of the tanks. After years of operation, this layer of sediment can become tens of centimeters thick, reducing the effective volume of the digester and lowering gas production efficiency. That is why biogas facilities must periodically carry out one of the most demanding maintenance operations in the entire plant: digester cleaning. Before any equipment can be brought inside, the tank must be isolated from the rest of the system and thoroughly inspected. Technicians measure methane, hydrogen sulfide, and oxygen levels to ensure the working environment is free from explosion hazards and dangerous gases. Once the digester has been declared safe, specialized mixing vehicles equipped with hydraulic booms stretching dozens of meters are positioned around the tank. Powerful agitators mounted at the end of these booms begin breaking apart sludge deposits that have accumulated over many years, mixing them back into the remaining liquid inside the vessel. When the material reaches a suitable consistency, maintenance hatches near the base of the digester are opened, and large-diameter industrial hoses are connected to heavy-duty vacuum trucks. Using extremely powerful suction, tens or even hundreds of cubic meters of settled sludge are extracted from the tank. The operation resembles a gigantic vacuum cleaner cleaning out an industrial stomach capable of holding thousands of cubic meters of material. The extracted sludge is then transferred to specialized storage tanks for further treatment or, depending on its composition, eventual reuse in agriculture. However, the job is still not finished. Even after the vacuum system removes most of the liquid sludge and loose sediment, a dense layer of material often remains at the bottom of the tank. This residue typically consists of sand, gravel, plant fibers, and other debris that has accumulated throughout years of operation. Once sludge levels have been reduced to a safe level, technicians bring compact skid loaders and specialized mini loaders into the digester. Inside a structure that normally remains filled with digestate, these machines scrape, gather, and push the remaining deposits into concentrated piles. The material is then loaded into containers or moved to centralized extraction points for removal. Only after the final layers of accumulated sediment have been cleared away does the concrete floor of the digester gradually reappear, often for the first time in many years. At that point, the massive artificial stomach is ready to be returned to service and begin another cycle of converting waste into renewable energy. After understanding how these massive digesters operate and how they are cleaned, another question emerges. How do engineers build an artificial stomach capable of holding nearly 10,000 cubic meters of waste, withstanding continuous pressure, and operating reliably for decades? The answer begins with the foundation, the structure responsible for supporting everything above it. Every megastructure begins by conquering the ground beneath it. To create space for 7 gigantic digesters, engineers first had to excavate a site covering an area comparable to several football fields. Tens of thousands of cubic meters of soil and rock were removed by fleets of heavy excavators and haul trucks. Viewed from above, these enormous machines appear as little more than tiny dots, working relentlessly to carve deep into the earth. The goal is not simply to create a hole, but to reach stable geological layers capable of supporting the immense loads that will eventually rest above. Once completed, each digester and its contents will weigh tens of thousands of tons, making a strong and stable foundation essential to prevent settlement, deformation, or structural damage over the decades of operation that lie ahead. Once the foundation platform is ready, construction of the tank base begins. This is far more than a simple concrete pour. The base must withstand the entire pressure of nearly 10,000 cubic meters of liquid above it. Hundreds of tons of reinforcing steel are arranged in a dense pattern, resembling a giant spider web. Soon after, fleets of concrete mixer trucks continuously deliver concrete into the excavation. The concrete must be poured in a continuous pour without interruption to prevent the formation of cold joints, potential weak points through which liquid could eventually seep. Once cured, the concrete forms a massive monolithic reinforced concrete foundation, as solid and durable as an underground fortress. From this massive foundation, the walls of the artificial stomach begin to rise. Rather than square or rectangular structures, all digesters are built as circular tanks. From an engineering standpoint, a circular shape is the most efficient way to evenly distribute the enormous pressure exerted by liquid slurry and biogas from within. To build these walls, engineers use massive slip-form systems or assemble precast concrete panels with millimeter-level precision. The joints are then sealed with highly flexible materials to ensure the structure is completely gas-tight. Any leakage of methane or hydrogen sulfide could create serious safety risks. As a result, these walls serve not only as the vessel where digestion takes place, but also as a protective barrier for the entire facility. Finally, to seal the system, engineers do not use concrete. Instead, the top of each digester is fitted with a double-membrane biogas dome. The inner membrane is made from highly durable synthetic materials that can withstand exposure to acids and biogas, while the outer membrane protects the structure from storms and the harsh Nordic climate. One of the most interesting features of this design is its flexibility. As trillions of microorganisms below produce biogas, the membrane gradually expands, swelling like a giant balloon. When the gas is extracted for upgrading, the dome slowly contracts again. This continuous cycle of expansion and contraction gives the entire facility the appearance of a living organism, constantly breathing as it produces renewable energy. Those giant concrete stomachs, no matter how impressive, would be nothing more than lifeless structures without the infrastructure that connects them. To transform them into a functioning system, engineers must build a complex industrial network capable of handling everything from receiving waste to delivering purified gas. If the digesters are the stomachs, then the pipeline network is the circulatory system of the entire facility. Tens of kilometers of corrosion-resistant steel pipes and durable-gauge DDPP pipelines are installed throughout the plant. Constructing this network requires exceptional precision. Digestate is highly viscous and can be chemically aggressive, so the pipelines must withstand both the pressure generated by powerful pumping systems and the demanding operating environment. They are also insulated to keep the material warm as it moves through the facility during the harsh Nordic winter. Viewed from above, the pipeline network forms a web of intersecting lines stretching across the complex, linking every section of the plant into a single integrated system. To feed more than 3,000 of waste into the system each day, engineers built a massive receiving hall with large underground concrete reception pits. One of the biggest challenges is odor control. The facility is designed as a sealed structure equipped with powerful negative pressure ventilation systems that continuously draw air inward, preventing odors from escaping. Here, waste is unloaded, processed, and begins its journey into the plant's giant artificial stomachs. After weeks of digestion, the biogas produced is still a raw gas mixture containing methane, carbon dioxide, and trace impurities. To turn it into pipeline-quality fuel, engineers build a gas upgrading unit. This facility consists of tall processing towers where carbon dioxide, water vapor, and other unwanted compounds are removed through specialized filtration and treatment systems. Acting like the plant's lungs, the upgrading system purifies the gas until the methane concentration reaches about 97%, making it comparable to conventional natural gas. This is the final step that completes the entire system. After leaving the upgrading facility, the purified biomethane is sent to a compressor station, where its pressure is increased before being injected into Denmark's national gas network. What began as livestock manure and organic waste is transformed into renewable energy that can be delivered across the country, helping heat homes and power businesses throughout the year. Korsgro is far more than a biogas plant. It is part of Denmark's strategy to strengthen energy independence and reduce reliance on fossil fuels. First, energy security. Because biomethane has properties similar to natural gas, it can be injected directly into the existing gas network. This allows Denmark to increase its supply of renewable energy without building an entirely new distribution system. Second, emissions reduction. Instead of allowing livestock manure and organic waste to decompose naturally and release methane into the atmosphere, biogas plants capture that energy and convert it into a useful fuel. Even the carbon dioxide removed during gas upgrading can be recovered and reused by industry. At the same time, the remaining digestate can be returned to farmland as fertilizer, creating a cycle in which waste becomes energy, nutrients, and industrial resources. For Denmark, biogas is not simply a source of renewable fuel, it is a key component of a more resilient and sustainable energy system. China is entering a battle against a wild army capable of turning entire fields into war zones overnight. Herds of wild boars, each weighing hundreds of kilograms, sweep into farmland, rooting through the soil like living plows and wiping out months of farmers' hard work. But this isn't just happening in China. From Germany and Spain to Texas in the United States, wild boar populations are exploding at a rate that's giving governments a serious headache. Countries have tried everything: electric fences, steel traps, professional hunting teams, even helicopters. Yet time and again, the boars return, nearly impossible to eliminate. However, the story takes an unexpected turn. Instead of treating wild boars solely as an agricultural disaster, China is finding ways to turn them into a high-value meat source and a new economic opportunity. So how did they do it? Let's find out with Mandarin Tech. Wild boars originally came from vast forests stretching across Eurasia and North Africa. However, today their range has expanded at a rate that truly concerns many ecologists. Their reproduction works almost like a natural multiplication machine. An adult female can give birth to 6 to 12 piglets per litter, and this happens twice a year. Within just a few years, a small group can easily triple in size if left uncontrolled. This explosive growth has turned wild boars from a normal wild species into one of the most troublesome invasive animals on the planet. In the United States, the wild boar population has now exceeded 6 million, spreading across more than 35 states. Texas alone is home to about 2.6 million of them, making it the wild boar capital of North America. During the day, they hide in forests, but when night falls, herds weighing hundreds of kilograms begin to flood into farmland. With snouts as strong as steel plows, they tear up the ground to search for roots, tubers, and insects while trampling everything in their path. In just one night, an entire field can be churned up, as if a convoy of farm machinery had passed through in the dark. As a result, the damage has reached a staggering scale. The United States Department of Agriculture estimates that wild boars cause around $2.5 billion in losses each year to agriculture and rural infrastructure. In California, vineyards in Napa Valley have been forced to build kilometers of electric fencing to keep boars coming down from the hills. In Spain, farmers in Catalonia often wake up to find their corn and wheat fields destroyed overnight. Meanwhile, in Germany, potato and barley fields around Brandenburg are frequently turned into chaotic patches of overturned soil with crops broken and scattered. Faced with increasingly severe destruction, many countries have been forced to launch large-scale control campaigns to deal with wild boars. In Europe, where the species is widespread from Spain to Germany and Poland, many agricultural regions have built kilometers of electric fencing to protect their fields. However, the largest scale control efforts are taking place in the United States, particularly in Texas and Oklahoma. Here, massive steel corral traps are set up along forest edges and cornfields. Each trap typically has a diameter of 10 to 15 meters, large enough to capture an entire herd at once. Inside, corn or fermented feed is used as bait, while motion-triggered cameras and remote control systems monitor every movement. When enough boars gather inside, a heavy metal gate weighing hundreds of kilograms is triggered to drop. In a single capture, 20 to 30 animals can be trapped inside one steel enclosure. When trapping alone can no longer keep up with population growth, professional hunting teams are brought in. In the southern United States, hunters track wild boars at night using thermal imaging and infrared equipment, allowing them to detect herds from hundreds of meters away. Some hunting operations can eliminate hundreds of animals in a single night, with hundreds of thousands removed each year across the country. In areas with extremely high densities, the hunt even moves to the skies. Helicopters fly low over fields and plains, while hunters shoot from above, chasing down herds scattering below. In Texas alone, this method removes tens of thousands of boars annually, making it one of the largest wildlife control operations in North America. Yet even with hundreds of thousands of wild boars killed each year, their population continues to rebound rapidly. While one group is eliminated in a field, others are still breeding and growing in nearby forests, making the battle between humans and this species seem as if it will never truly end. While many countries see wild boars as pests that must be eliminated, China looks at them in a completely different way. Not as enemies, but as a high-value food source. In many mountainous regions of southern and southwestern China, wild boar meat has long been considered a delicacy. Compared to industrially farmed pork, this meat is firmer, leaner, and has a richer, more distinctive flavor. As a result, on the market, wild boar meat often sells for 2 to 3 times the price of regular pork. After the major shock to the livestock industry caused by the African swine fever outbreak in 2018, when hundreds of millions of pigs in China had to be culled and meat supply dropped sharply, many farms began searching for new directions. One of these was crossbreeding wild boars with domestic pigs, creating hybrids that retain some of the wild flavor while adapting better to farming conditions. From there, a new farming model began to take shape. In mountainous provinces such as Guangxi, Hunan, and Guizhou, many farms have enclosed entire hillsides and large forest areas with tall steel fencing. Each enclosure can span 20 to 50 hectares, large enough for herds to move in an environment that closely resembles the wild. Instead of being confined in concrete pens, the animals are released in groups, running across slopes, digging into the soil for roots, forest tubers, and insects beneath layers of leaf litter. Some large farms in Guangxi now raise between 3,000 and 5,000 animals in these controlled forest environments. The need to run on hillsides, dig for food, and forage throughout the day keeps them active almost constantly, resulting in meat that is noticeably firmer and leaner. one of the key reasons wild boar meat remains highly sought after in the specialty market. The difference is therefore striking. In industrial farms, pigs grow up in enclosed pens, fed fixed diets, and barely move. But in these forested hills, the herds run, dig, compete for food, and move continuously as they would in nature. They retain almost all of their wild instincts, except now, those instincts exist within a controlled farming system. In these semi-wild farming systems, the pig's diet is simple but highly effective. Instead of relying entirely on expensive industrial feed, farmers make use of common agricultural products such as corn, cassava, sweet potatoes, rice bran, and soybeans. Food is scattered across multiple locations in the forest or placed at fixed feeding points, forcing the herd to move, dig, and forage every day. By utilizing local crops and agricultural byproducts, feeding costs are significantly reduced compared to industrial pig farming. As a result, the growth rate of hybrid wild boars is slower. It typically takes about 12 to 18 months for one to reach market size. However, when fully grown, many can weigh between 120 and 150 kilograms, with long bodies, broad shoulders, and well-developed muscles, traits that create the firm texture and rich flavor highly valued in the specialty meat market. At the same time, the herd retains strong reproductive capacity, allowing farms to expand quickly without high breeding stock costs. After about a year, the pigs are sorted based on purpose. Strong and well-developed individuals are kept for breeding, while the majority are sent to market and supplied to processing facilities or specialty restaurants. Thanks to low feeding costs, strong reproduction, and attractive selling prices, wild boar farming in China has gradually developed into a market worth around $5 billion per year, turning a species once seen as an agricultural disaster into a significant source of income for many rural areas. But does turning wild boars into a farming industry truly solve the problem? Or is it simply creating a new, more complex challenge for the future? In this world where flavor is not only created but also nurtured over time, everything begins with how the raw materials are handled. After being brought into the facility, the pigs are carefully cleaned and broken down. The legs are directed toward whole-cured products, while the highest quality lean cuts are set aside, becoming the core ingredient of salami. From here, the process takes a completely different path. The lean meat is thoroughly cleaned, cut into small pieces from selected cuts, and fed into a high-capacity grinder where the muscle fibers are finely processed, laying the foundation for the final texture. At the same time, white fat, tender loin, and a small portion of offal are added to the mixture. These elements not only enhance richness, but also balance and deepen the flavor. Once the mixture reaches the desired grind, the mixing stage begins, where identity is shaped. The meat is blended in industrial mixers with sea salt, black pepper, white wine, garlic, and spices such as fennel or paprika, depending on regional style. Each producer keeps a unique recipe. Even slight variations can create a distinct signature. Despite the use of machinery, artisans still rely on their senses to control texture and aroma. After seasoning, the mixture is transferred to a hydraulic stuffing machine. Cleaned and lightly salted natural casings are fitted onto the nozzle, and under controlled pressure, the meat is evenly filled into the casing, forming salami with just the right firmness, tight enough to hold structure, but not so dense that it traps air pockets. Each salami is then tied by hand using traditional techniques. Even though the production line can produce hundreds of units per day, this manual step preserves the soul of the process. Once shaped, the salami enters its most critical stage, fermentation and curing. The curing rooms are designed as controlled microclimates, maintaining temperatures between 12 and 16 degrees Celsius and humidity levels of 70% to 80%. Over the next 3 to 6 weeks, lactic acid bacteria work silently, transforming raw meat into salami with a slight tang, a darker color, and a complex aroma. A thin white layer of mold gradually forms on the surface. Not a sign of spoilage, but a natural protective coating that helps retain moisture and regulate oxygen. Each day, workers carefully rotate every salami to ensure even drying and consistent structure. This stage demands absolute patience, where even a small mistake can ruin an entire batch. When the salami reaches its ideal maturity, it moves to the finishing area. Here it is cleaned by hand to remove excess mold, labeled with the production date, and wrapped in specialized food-grade packaging. Some premium products are additionally wrapped in wax paper to preserve their traditional character. Finally, the finished salami is packed into cartons and leaves the facility, beginning its journey to high-end culinary markets around the world, where every slice continues to tell a story of time, technique, and human craftsmanship. Alongside salami, cured pork leg also carries a rich and irreplaceable flavor. The legs are brought to the manual cutting area, where experienced craftsmen shape the product with slow and precise movements. Excess fat and skin are removed just enough to allow the salt to penetrate evenly while preserving the traditional structure of the ham. Before the salting process begins, each leg is assigned a unique identification code, like its identity throughout the curing journey. They are then moved into cold, dark rooms where temperature and humidity are carefully controlled. Here, each leg is completely covered with pure sea salt and remains almost motionless, while the salt gradually penetrates deep into the muscle fibers, drawing out moisture and initiating the development of flavor. After salting, the legs move to the shaping stage. A continuous roller system gently compresses the muscle fibers, allowing the salt to penetrate deeper without damaging the natural structure. Next, they are washed with high-pressure cold water to remove excess salt, while the absorbed flavor remains inside. The legs are then shaped using specialized presses to refine their curves and proportions. Once completed, they are hung and transferred to special curing rooms, where controlled environmental conditions begin the natural flavor development process. During the first 90 days, the cool and humid environment allows the outer skin to stabilize gradually, while the inner meat becomes more concentrated. This process happens slowly, without mechanical intervention, under the careful supervision of skilled workers. Next, the legs are transferred into curing cellars, a quiet environment where they remain for 24 to 36 months. During this time, natural enzymes gradually break down proteins and fats, creating a distinctive flavor that cannot be replicated by technology. The product loses about 30 to 40% of its weight, but in return gains significant quality and value. When the ideal level of curing is reached, each ham is manually inspected using traditional methods to ensure perfection. They are then moved to the finishing stage, where the bones are removed and the meat is trimmed to achieve an attractive shape and convenient form. Finally, the product is packaged using vacuum sealing or sliced by high-capacity automated systems. The thin slices are carefully arranged, sealed, and packed into cartons, ready to be distributed to high-end markets around the world, where each slice carries the value of time, technique, and human craftsmanship. More than 200 kilometers of entirely new metro lines, 68 underground stations, and nearly 20 giant tunnel boring machines are operating simultaneously beneath the heart of Paris, one of the most complex cities in Europe. Right below historic boulevards that are over a century old, France is building a completely new underground transport network, large enough to be considered a second metro city, forming in parallel with the Paris we see today. After more than 120 years of operation, the original metro system, designed for a previous century, is becoming the biggest bottleneck for a metropolitan region of over 12 million residents. So how can such a massive metro network be constructed beneath one of the most complex urban environments in Europe? Let's explore the answer together with Mandarin Tech. Grand Paris Express is an entirely new transport network being built almost from scratch beneath the Paris metropolitan region. When completed around 2030, the system will include 4 fully automated lines: Lines 15, 16, 17, and 18. To make this network possible, dozens of deep construction shafts have been opened right in the middle of existing residential areas, allowing a large number of tunnel boring machines to operate simultaneously underground. At the same time, around 600,000 precast concrete segments are being continuously manufactured to form the protective lining of the entire new tunnel system. Many of the stations are being built at depths comparable to multi-story buildings and will connect directly with the existing metro and RER networks, creating a completely new cross-regional transport structure. Once in operation, the network is expected to serve around 2 million passengers every day, making Grand Paris Express the first major orbital transport backbone that allows suburban areas around Paris to connect directly with one another, without having to pass through the city center, as commuters have been forced to do for more than a century. Before the first tunnel boring machine even began to rotate, Grand Paris Express had already become one of the most complex infrastructure preparation campaigns ever carried out in Europe. Unlike metro projects built in undeveloped areas, most of the new lines had to pass through urban districts that have existed for hundreds of years. This meant that before digging underground could begin, the entire surface environment above had to be reorganized. Hundreds of land parcels were acquired. Many existing structures had to be demolished. Several roads and utility systems were temporarily relocated to make space for construction shafts. In the Archaea Kashan area, to prepare the connection between the new metro line and the existing RER network, a massive steel structure weighing about 3,000 tons was pre-assembled and then slid sideways nearly 26 meters in just a few hours. This marked the starting point of one of the largest underground construction operations ever deployed in a densely populated urban environment. If the tunnels are the structural backbone of the Grand Paris Express, then the stations are the strategic anchor points that determine how efficiently the entire system operates. Most of the Grand Paris Express stations are built using a controlled cut-and-cover construction method. First, engineers construct reinforced concrete diaphragm walls around the perimeter of each future station site. Deep trenches are excavated in advance, steel reinforcement cages are lowered into place, and concrete is poured to form a stable structural frame that protects the entire construction zone. Only after this protective box is completed can the soil inside be excavated layer by layer in a carefully planned sequence. Alongside structural requirements, engineers also had to solve another critical challenge: minimizing transfer time between lines. For this reason, both the location and elevation of each station are designed to keep connection distances to existing metro and RER lines as short as possible. Tunnel boring machines, or TBMs, are the primary force responsible for creating the entire underground tunnel network of the Grand Paris Express. In this project, more than 20 giant TBMs operate simultaneously beneath the city of Paris, forming one of the largest underground construction campaigns ever carried out in a dense urban environment. Each TBM is about 100 meters long, with a cutter head nearly 10 meters in diameter. This is not just a drilling machine. It is essentially a mobile underground factory capable of excavating soil, transporting materials, and installing tunnel lining segments directly behind the cutter head in one continuous working cycle. At the front of the TBM is the massive cutter head, which breaks through the soil and rock ahead of the tunnel path. Depending on the geological conditions, the cutter head is equipped with different tools, ranging from scraping blades designed for soft ground to heavy-duty disc cutters used for harder rock layers. Although the cutter head is extremely large, it rotates quite slowly, usually only a few revolutions per minute. However, the force it generates is enormous, powerful enough to break through geological layers located dozens of meters below the surface. Once the ground is excavated, the material is transported backward through a giant screw conveyor system, then transferred onto conveyor belts running along the body of the machine to carry it out of the tunnel. This entire process operates continuously, turning the TBM into a fully integrated construction system that can advance forward meter by meter while still maintaining safety for the dense urban environment above. right behind the tunnel boring machines. The concrete lining of the tunnel must be installed continuously to ensure the long-term stability of the entire structure. This lining is made up of precast reinforced concrete segments known as voussoirs. Across the entire Grand Paris Express network, about 600,000 of these segments will be produced to form the protective structure for more than 170 kilometers of underground tunnels. Each segment weighs between 4 and 9 tons, and 7 segments are assembled together to create one complete tunnel ring. The production process begins with cleaning the molds and applying a release agent to ensure the segments can be removed easily after curing. Next, waterproof gaskets are precisely installed inside the molds to guarantee the watertight performance of the tunnel rings once assembled. After that, the reinforcement cage is placed into the mold, forming the main load-bearing framework of each segment. Once all components are in position, concrete is poured into the mold and compacted using pneumatic vibration equipment to ensure an even distribution throughout the entire volume. The molds are then moved into curing chambers, where temperature and humidity are carefully controlled to accelerate the hardening process. After only a few hours, the segments can be removed from the molds and transferred to the storage area. Thanks to this continuous production system, a new concrete segment is completed roughly every 10 minutes, fast enough to keep pace with the excavation progress of multiple underground construction fronts operating simultaneously beneath Paris. It is the multifunctional tunnel boring machine itself that turns individual concrete segments into a precisely engineered geometric structure running deep beneath the city of Paris. Each segment is lifted into position by robotic arms and installed according to a carefully calculated sequence. Once the tunnel ring is closed, the machine uses this newly installed concrete ring as a reaction surface to push its entire body forward by about 2 meters. However, the real challenge is not simply creating straight tunnels. Paris is a layered maze of infrastructure: ancient foundations, older metro lines, sewer networks, and historic structures. To avoid these obstacles, the tunnels of the Grand Paris Express must constantly change direction as they move through the underground environment. This is achieved by carefully adjusting the geometry of each segment ring. With only very small changes in the installation angle between the concrete segments, the TBM can create large radius curves while still maintaining watertight performance and structural stability. Thanks to this technique, the tunnel alignments can curve precisely beneath the city without affecting the structures above the surface. In fact, beneath Paris lies an extremely complex underground environment that has developed over many centuries. In addition to the existing metro lines and modern technical infrastructure, this area also contains numerous old limestone quarries and natural voids that could create subsidence risks if they are not treated before construction begins. Before tunneling machines pass through these areas, engineers must first inject grout into the underground cavities to stabilize the soil. This process is carried out by drilling small boreholes from the surface down to the zones that need reinforcement, then pumping liquid material into the voids to completely fill the empty spaces. However, for a project stretching across hundreds of kilometers, like the Grand Paris Express, engineers deployed a terrain deformation monitoring system based on radar satellites, one of the most advanced monitoring technologies ever applied to an urban infrastructure project. Approximately every 11 days, the TerraSAR-X satellite passes over the project area along the same orbital path and sends radar signals toward the Earth's surface. Thanks to this radar interferometry technology, tens of thousands of measurement points per square kilometer can be monitored simultaneously throughout construction. This allows engineers to detect even the smallest ground deformations early and adjust construction activities before they develop into real risks. Within the entire Grand Paris Express network, Saint-Maur-Créteil station is the deepest station ever built in France's underground transport system. Located about 52 meters below ground level, roughly equivalent to the height of an 18-story building. Constructing a station at such a depth created a major challenge for passenger accessibility. How could people move quickly between street level and platforms located more than 50 meters underground? The solution was a system of 11 high-speed elevators capable of transporting passengers to this depth in about 15 seconds, making it one of the fastest vertical access systems in the modern French metro network. The station structure itself is also highly unusual. Instead of the traditional rectangular layout, Saint-Maur-Créteil was designed with a dual parallel chamber configuration shaped like a peanut, which helps optimize construction space in complex geological conditions, while also distributing loads more efficiently along the tunnel walls. These engineering challenges clearly demonstrate how designers had to adapt to some of the most demanding underground conditions beneath Paris in order to build a completely new metro network for the 21st century. But at this point, you may be wondering what actually led to the creation of the Grand Paris Express. To understand that, we need to go back to 1900, the year when Paris opened its very first metro line. At that time, the underground network was designed with a very clear logic to bring passengers into the city center. The metro lines functioned like spokes converging toward the historic urban core, where most of France's population, jobs, and economic activity were concentrated. For many decades, this structure worked efficiently, but by the end of the 20th century, Paris had changed completely. Millions of people began living in the suburbs, while research centers, airports, universities, and new economic zones were spreading across the wider Île-de-France region. As a result, the historic urban core gradually became a major bottleneck for a metropolitan area of more than 12 million residents. In fact, the idea of building an outer orbital metro network had already been proposed by earlier generations of planners. However, the enormous cost and shifting urban planning priorities caused the project to be delayed repeatedly. It was only in the early 21st century, when transportation pressure reached its limits and Paris urgently needed an entirely new connectivity structure, that the plan was finally revived. When completed, the Grand Paris Express network is expected to serve around 2 million passengers each day, creating direct rail links between suburban districts that once depended heavily on private cars. By shortening travel times across the Île-de-France region, the system will not only ease congestion in central Paris, but also significantly reduce transport-related emissions across the wider metropolitan area. At the same time, the project is transforming the urban landscape far beyond the tunnels themselves. Dozens of new districts are being planned around future stations, turning previously disconnected areas into emerging hubs for housing, universities, research centers, and business activity. These developments follow a high-density yet environmentally conscious planning model designed to support long-term regional growth. Even the massive volume of excavated material, about 45 million tons of soil removed during tunneling, is being reused for land reclamation, infrastructure platforms, and landscape restoration projects, ensuring that much of what was taken from beneath Paris is returned to shape its future surface. Amid the harsh desert climate of Dubai, where temperatures can melt human willpower, the Burj Khalifa rises like a spear of steel and glass, piercing straight into the Middle Eastern sky. This is the tallest tower in the world, so tall that people believed it would collapse under its own weight, challenging the weak geology, being tested under 50-degree heat, and facing winds stronger than sea storms. A structure that once made the whole world ask, is anyone crazy enough to build it? But what makes the Burj Khalifa a legend does not lie only in its record-breaking height, but in the entire journey of building it. In today's video, Mandarin Tech will help you decode how the Burj Khalifa was created in the harsh desert, and why, even until now, it still stands proudly as the ultimate symbol of modern engineering brilliance. The story truly begins with Dubai's silent crisis. When the Burj Khalifa rose to its astonishing height of 2,617 feet, it not only shattered architectural records, but also marked a turning point in the UAE's development strategy. For decades, the economy here relied heavily on oil. But as reserves gradually declined, Dubai was forced to find a new path, becoming a global city that attracts tourism and investment. The idea of building the tallest structure on the planet came from that very ambition. If Dubai wants to be remembered by the world, the planner said, it needs a symbol that anyone would want to witness with their own eyes. And with its strategic position between Europe and Asia, the busiest air transit crossroads in the world, Dubai had the foundation to turn this bold vision into reality. To ensure the tower would not only exist, but become the centerpiece of an entirely new city, Dubai launched a construction plan of unprecedented scale. More than 12,000 workers from over 100 countries worked in shifts around the clock. The Burj Khalifa emerged as a powerful declaration. Dubai would not simply survive the post-oil era, it would shape its future with intelligence, ambition, and world-class engineering. When engineers first surveyed the construction site of the Burj Khalifa in 2003, the area was nothing more than a vast expanse of sand, empty and almost completely without natural bedrock. Results from drilling hundreds of feet deep revealed that beneath the sand was not granite or solid limestone, but calciciltite, a weak sediment formed from compressed shell powder. This material is brittle, easily fractured, and extremely unstable, considered one of the worst possible conditions for the foundation of a super tall building. Construction history has already shown the consequences of misjudging foundations, such as the Leaning Tower of Pisa, due to its shallow foundation on sandy soil. Those structures are all much shorter than the Burj Khalifa. For the Burj Khalifa, its enormous load would be transferred to the weak ground through the foundation system. If the foundation were not designed correctly, even a small error could cause dangerous differential settlement. The question was, how could the tallest building in the world stand firmly on the weakest ground? For a structure like the Burj Khalifa to stand on its own, simply scaling up the design of conventional high-rise buildings was impossible. The engineering team had to create an entirely new foundation system, one strong enough to support a structure weighing more than 500,000 tons on the weak desert soil. With no bedrock to anchor into, they designed a massive raft foundation, 12 feet thick, buried 24 feet deep, and covering 80,000 square feet. The raft foundation acts like a large board that spreads the entire load over a wide area, reducing pressure on the soft soil beneath. Just as flat-soled shoes do not sink into grass while high heels dig deep, the raft foundation helps the tower remain stable even without solid rock to rely on. Even though the raft foundation distributes load very effectively, it still needed to be anchored firmly to resist lateral movement caused by wind and soil deformation. Therefore, the engineers added a friction pile system consisting of 194 concrete piles, each 5 feet in diameter and drilled to a depth of 164 feet. The remarkable thing is that these piles do not reach bedrock because the area has no solid rock layer at an appropriate depth. They rely entirely on friction between the pile surfaces and the weak sedimentary soil to stabilize the entire structure. Although each pile does not provide immense resistance individually, the combined effect of hundreds of them creates extraordinary lateral strength, sufficient to secure a tower weighing more than 500,000 tons. Settlement measurements after completion were only about 40 to 50 millimeters, an impressive figure for the tallest building in the world, proving that the foundation system performed exactly as designed. The next challenge lay in building a structure more than half a mile tall using cast-in-place concrete. As the tower continued to rise, the biggest problem emerged: how to pump concrete to nearly 1,965 feet, a height that had never been achieved before. At this level, the concrete would remain inside the pipe for more than half an hour, long enough for it to begin setting and potentially ruin the entire system. To solve this, the engineers developed a special concrete mixture with admixtures that preserved workability for an extended period. The concrete was mixed with ice water to reduce its temperature and pumped only at night to avoid the outdoor heat above 104 degrees Celsius, which would cause the material to harden too quickly. The world's most powerful Putzmeister pumps were deployed, capable of pushing concrete nearly 1,965 feet in a single pumping operation, setting a new record in the construction of super tall buildings. Parallel to the challenge of pumping concrete, the engineers faced another issue. The central concrete core became too slender as the height increased dramatically. The solution was inspired by ancient Gothic architecture, where buttress walls were used to stabilize cathedral structures. The Burj Khalifa applies this principle by adding 3 large buttresses radiating from the central core, forming its distinctive Y-shaped plan. These 3 wings distribute compressive forces across the entire raft foundation, reduce torsion, and enhance wind resistance. This was the first time a 3-buttress structural system had ever been used for a skyscraper, and it became the fundamental reason why the Burj Khalifa could continue rising while maintaining the stability it needed. As the tower rose into the sky, the working environment became extremely dangerous. Workers were transported to higher floors using steel cages that moved along the structure. Even so, a small number of workers lost their lives during construction. Even after the building was completed, those responsible for maintenance, such as the rope-suspended window cleaning crews, still had to face unpredictable risks. They hang themselves by 3 ropes in midair, working in strong winds that can reach more than 19 knots. When the wind exceeds the permitted limit, all work must stop immediately to ensure safety. Cleaning the entire glass facade of the tower takes up to 3 months, and all of it is done manually, mostly by workers from Nepal, where mountain climbing is almost a tradition. A silent but crucial component is the series of mechanical floors. These mechanical floors are the backbone that helps the entire building stand firm against storms and its own enormous weight. These are special technical levels arranged intermittently along the tower and can be identified by the dark bands on the exterior. Inside, they function as rigid planes, connecting the forest of concrete steel columns with the hexagonal central core, helping to distribute wind forces, reduce torsion, and prevent the structure from bending. These floors also house electrical systems, water tanks, and essential technical equipment, while providing anchor points for the facade cleaning teams. The higher the tower rose, the more it had to confront another major enemy: wind. In the Arabian desert, massive sandstorms can engulf the entire sky. During the summer, northwesterly winds frequently reach more than 50 miles per hour, exerting enormous pressure on a structure as tall as the Burj Khalifa. Instead of using counterweights, the builders decided to attack the root of the problem directly. The wind force had to be reduced from the very beginning. The solution lay in the tower's shape. They designed the Burj Khalifa in the form of 3 petals, resembling the desert flower himinocalis. A 3-wing floor plan, tapering as it rises, with the floors subtly rotated into a spiraling form. Thanks to the continuously changing shape with elevation, the wind can never form a synchronized vortex over the entire building. Instead, it breaks into small, scattered vortices that are not strong enough to pose a threat. Another remarkable feature is that the Burj Khalifa has an emergency elevator with a travel distance of 138 floors, the longest in the world. Contrary to the rule that, during a fire, elevators must not be used, this elevator is encased in an extremely thick, fire-resistant concrete layer and can bring 26 people down to the ground in less than 1 minute. In addition, the engineers designed a system of safe refuge areas, sealed, smoke-proof rooms with fresh air supply, distributed throughout the tower. When a fire occurs, the pressurization system pumps clean air into the stairwells, creating an invisible barrier that prevents smoke from entering. All of this ensures that even at the 160th floor, people inside still have enough time and safety to wait for rescue or evacuate in a controlled manner. When the tower reached nearly 1,500 feet, workers began installing the glass cladding, the skin of the building. Each glass panel, 26,000 in total, was installed manually over 2.5 years. The glass surface area is enough to cover 20 football fields. But this shimmering facade brought a serious problem. Dubai's weather can exceed 49 degrees Celsius. Without proper treatment, the inside of the tower would turn into a boiler within hours. The solution lay in the metal-coated technology applied to the glass surface, which reflects more than 70% of solar heat. What you see glittering on the Burj Khalifa is solar energy being reflected away instead of entering inside. Even so, glass alone is not enough to cool a city in the sky. The tower has more than 65 million cubic feet of air that must be cooled continuously, and miles of air ducts along with massive mechanical floors filled with pumps powerful enough to inflate 13 hot air balloons every minute. By 2008, when the Burj Khalifa had already surpassed every record and become the tallest structure in the world, one part was still unfinished. The metal spire more than 700 feet tall. The problem was that no crane on Earth was tall enough to install it from the outside. Therefore, the engineers chose an unconventional solution, assembling the entire spire inside the tower. They built each segment of the spire right within the hollow space of the building, then used a jacking system to push it upward, gradually along the vertical axis. When the final metal tip pierced through the top, the Burj Khalifa reached its ultimate height, 2,717 feet. No structure on the planet even comes close to this height. When you look at the entire city of Dubai below, you will understand that you are witnessing one of the greatest engineering feats in human history. But when a building rises high enough to touch the clouds, it becomes the target of the sky's most dangerous force: lightning. People often joke that the Burj Khalifa is Dubai's lightning rod, but that statement is entirely serious. The tower has been struck by lightning at least 18 times since it was completed. To protect the entire structure, the engineers designed a special lightning protection system at the top of the tower. This system uses sensors to detect when a lightning strike is about to occur and releases a trigger arc to attract the electrical discharge to the exact point needed. But protecting only the pinnacle is not enough. Therefore, the entire metal frame of the Burj Khalifa is designed as a Faraday cage, guiding the electrical current down to the ground along the exterior shell instead of letting it enter the interior spaces where people and electronic equipment are located. At a time when 41% of Earth's land has already been swallowed by expanding deserts, China has suddenly become the center of one of the boldest ecological comebacks of the century. And the solution isn't high-tech, nor is it a miracle. It's 200 million willow trees and 1.2 million rabbits. These harmless-looking rabbits carry a strange natural mechanism powerful enough to change the fate of an entire landscape. Behind this seemingly crazy idea is a man once known as the madman of the desert, someone who believed that with the right ecological loop, even dead land can be brought back to life. And the place he chose for his experiment was Kubuchi, a region that used to have villages and green grasslands before fierce winds stripped away the topsoil and turned it into a 7,200 square mile sea of dead sand. So how could willow trees and rabbits reverse a disaster that science itself once considered hopeless? This story is one you won't be able to look away from. Today, Kubuchi is considered one of the harshest regions in all of China, a place where winters cut like a knife, dropping to minus 20 degrees Celsius, and summers get so hot they can scorch the ground. But this extreme climate is really just the surface of a much bigger disaster: desertification. According to a 2025 report, about 27.4% of China's land has already suffered severe degradation, an area nearly 4 times the size of Texas. Once vegetation disappeared due to overgrazing, deforestation, and exhausted farmland, the topsoil lost its anchor. Rising temperatures dried the surface even more. Strong winds then easily swept everything away, causing China to lose nearly 20 million tons of crops to the sea of sand every year. In just a few decades, sand dunes as tall as 60 meters pushed more than 40 kilometers eastward, burying thousands of acres of farmland and turning what was once a thriving region into one of the country's largest expanding deserts. Faced with the rapid spread of desertification, China launched large-scale campaigns as early as the 1950s and 1960s. They planted long belts of windbreak forests, restricted grazing, and drilled countless deep wells through layers of dry, loose soil in search of groundwater. But despite enormous effort and investment, the results were barely noticeable. The desert kept pushing south and northwest, threatening the livelihoods of more than 400 million people living in semi-arid regions. In the middle of that deadlock, a turning point came from the last place anyone expected. An ordinary man named Wang Wenbao, later known as the Desert King. Wang didn't come from money. He was a poor school teacher in Inner Mongolia, biking more than 10 kilometers every day across sand-covered roads just to get to school. Some mornings the wind was so strong that half his bicycle would be buried in sand, and waves of sand sharp as blades would lash his face and fill his lungs. In that harsh environment, Wang made himself a bold promise. If I can't escape the desert, then the desert will have to support me. No one imagined that this single sentence would become the starting point of a journey that changed an entire landscape. At the beginning of this journey, Wang Wenbao had almost nothing besides a small salt business and a determination that pushed against every limit. Yet he chose a path no one else dared to take. He emptied his entire savings, even borrowed money from friends and banks, all to chase a goal that sounded unbelievable, turning dry, lifeless sand into soil that could sustain life again. Many called him insane. Even the local authorities saw Wang as a dreamer, willingly throwing himself into the desert. But instead of backing down, Wang did the exact opposite. He moved straight into the heart of the dunes, facing the scorching winds and endless sand head-on. Every day, he carefully recorded the faintest traces of moisture left in the soil, watching how each gust of wind carved the terrain. As if he were trying to decipher a secret language the desert had been hiding for centuries. Step by step, he began tackling tasks that seemed impossible, building long stretches of windbreak walls, planting more than 60 million willow trees to anchor the land, and gradually restoring 1,300 square kilometers of barren terrain, all funded by hundreds of millions of dollars he somehow managed to assemble. But the real turning point only came when Wang conceived an idea no one had ever dared to imagine, bringing rabbits into the desert to create an entirely new ecological loop. When the idea of using rabbits to revive the desert first began to take shape, Wang understood one thing clearly. For the rabbits to survive, he first needed a plant strong enough to stand its ground against scorching winds and shifting sand. Out of dozens of options, only one species met every harsh requirement: the willow. Willows became the foundation of the entire ecosystem because their roots can reach nearly 90 meters deep, tapping into water layers that most plants can't reach. Once those roots take hold, they stabilize the sand, weaken the force of the wind, and create a cooler microclimate stable enough for life to begin. That's why the willow wasn't just another plant. It was the starting switch for the entire ecological loop. To turn willows into the backbone of the ecosystem, Wang had to face a challenge that had gone unsolved for centuries. How do you keep a tree alive in a place where the ground gets hot enough to scorch insects in minutes? In Kubuchi, the wind doesn't just blow. It carries sand like razor blades, capable of stripping bark and ripping out roots in just a few days. On top of that, surface temperatures above 70 degrees Celsius make germination almost impossible. That's why planting a willow here isn't as simple as dig a hole and drop in a tree. It's a constant battle with nature. Planting teams have to track faint pockets of moisture hidden beneath the sand, the last lifelines of the land. When they find a spot that can hold water, they dig deep pits and immediately shield them with wire mesh, reeds, and temporary barriers to protect them from the next strong gust of wind. The young willows are treated with special moisture-retaining solutions and anchored with wooden frames so they won't be ripped out overnight. Water has to be used sparingly. Drip irrigation delivers only enough for the roots to sense life and push themselves deeper into the soil, clinging to the earth. clinging to their only chance of survival in this harsh sea of sand. Once the first bands of willow trees grew large enough to cast shade and retain moisture in the soil, Wang introduced the most important link in his restoration model, bringing Rex rabbits into a closed, controlled ecosystem. These rabbits were never released into the wild. They were raised in tightly managed ecological farms, where each one had both economic and ecological value. Their meat became a clean food source, their fur was used in high-end fashion products, and their organs supported traditional medicine. But what truly turned the Rex rabbit into an ecological weapon was its droppings. Rabbit manure is extremely rich in nitrogen, phosphorus, and potassium, nutrients the desert lacks entirely. When released into the environment, it doesn't just fertilize the soil, it helps loose sand bind together into a moist, nutrient-rich layer of humus. Even more interesting, Rex rabbits cannot digest grass seeds. So every time they dig or forage, intact seeds end up mixed in their droppings and get scattered across the land, each one wrapped in a natural fertilizer pouch that allows it to sprout even under brutal desert conditions. As a result, new vegetation keeps appearing on its own, expanding the green coverage with minimal human intervention. Thanks to the arrival of the Rex rabbits, the structure of the new ecosystem gradually became clear and began operating like a self-balancing machine. The willow canopies provided shade and a steady source of food for the rabbits. The rabbits, in return, gave the land what it lacked most: nutrient-rich humus. This new soil held moisture, reduced erosion, and became the foundation for even stronger willow growth. This closed loop turned every hectare of sand into a natural humus-producing factory, generating more than 5 tons a year. Enough for a once barren, rock-hard stretch of desert to transform into fertile farmland in just 3 to 5 years. When the model scaled up, more than 200 million willow trees formed a massive green barrier, cutting wind speeds by up to 90% and preventing over 15 million tons of sand from shifting each year. Areas that were once helpless against sandstorms have now been restored with greenery across 700 to 800 square miles, creating a solid foundation for expanding the Rex rabbit farming model. As the ecosystem stabilized, the population of 1.2 million Rex rabbits not only helped regenerate the soil, but also became an economic spearhead, generating over 100 million yuan each year and providing thousands of families with a sustainable source of income in a place once considered uninhabitable. After the willow and rabbit ecological model proved successful, Wang Wenbao pushed his vision even further with a bolder step, combining land restoration with renewable energy. That's how the Junma solar power plant was born. A project that wasn't just economically meaningful, but also became a symbol of how humans can rebuild a desert. On land once too hot to walk on barefoot, 196,000 solar panels were arranged in the shape of a galloping horse, creating the world's largest energy mural, officially recognized by Guinness. Each year, Yunma generates 1 to 1.5 billion kilowatt hours of electricity, enough to power more than 200,000 nearby residents. But what makes the project truly special isn't just its output. The solar panels, spread across thousands of acres, cast a vast shadow that cuts wind speeds by up to 50%, retains surface moisture, and creates ideal conditions for grasslands to naturally recover. Once the grass returned, Wang used rabbits, sheep, and geese as biological lawnmowers, keeping vegetation under control while continuing to stabilize the soil. Between 2010 and 2020, this eco-economic model generated 10 billion US dollars, turning Kubuchi into the most profitable green development project in Asia. By 2022, Junma had saved 760,000 tons of coal, reduced CO2 emissions by 1.85 million tons, and restored more than 2,600 acres of land in just 4 years, a pace of recovery few ever believed was possible. Kubuchi's recovery isn't just something you can see as green patches returning on a map. It's backed by hard data that has genuinely surprised scientists. According to China's Ministry of Ecology, populations of wild deer, desert foxes, and migratory birds have increased fourfold compared to 1990. a rise never recorded in any other semi-arid region of the country. Species once believed to have vanished from Kubuchi are now reappearing, almost as if the entire ecosystem is rewriting its own story of survival. One of the most striking indicators of this comeback is the groundwater. Over the last 2 decades, water levels have risen by 1.5 to 2 meters, enough to completely change daily life for local residents. In the past, households had to drill extremely deep wells just to reach water. Today, they only need to drill about half as deep, cutting both costs and risks for the community. At the same time, native vegetation has surged back with remarkable strength. More than 100 plant species, from soft feather grass to resilient desert poplars to bright wildflowers, have returned across the landscape. Green bands now weave through the golden dunes, creating scenes that once seemed unimaginable. Small pockets of newly formed forest shimmering under the sunlight, growing right on land that was long believed to be nothing more than a dead sea of sand. Although Kubuchi's achievements are undeniably impressive, the model has also sparked considerable debate among experts. Some specialists argue that the role of the Rex rabbits has been overstated. In their view, the real driving forces are large-scale national planning strategies, massive financial investment, and a tightly managed ecological infrastructure maintained over many years. In addition, several pilot areas have reported unexpected side effects. The buildup of rabbit manure has caused nitrogen levels in the soil to spike, leading to nutrient imbalance. In a few ponds, wetlands, and temporary water bodies, outbreaks of green algae have been observed, raising questions about whether this model can remain stable in the long run, especially if it's expanded into regions with different soil structures. These debates become even more interesting when Kubuchi is compared to one of the world's classic cautionary tales, Australia's rabbit disaster. In the 19th century, just 24 rabbits were brought to the continent for sport hunting, but within less than 50 years, they multiplied into more than 1 billion. They devastated grasslands, uprooted shrubs, and turned nearly 2/3 of the plains into desert-like barren land. The Australian government tried everything, building a 3,200-kilometer fence, releasing viruses, using explosives, and even carrying out massive extermination campaigns. Yet nothing could stop the rabbits' explosive reproduction. The difference between Australia and China lies in the approach. In Kubuchi, the rabbits are never released into the wild. They are managed within a closed ecological system where every individual is closely monitored and serves a specific purpose, providing natural fertilizer, helping regenerate the soil, and generating economic value for local communities. Because of this difference in approach, the Kubuchi model gradually began attracting international attention. Although debates about its long-term sustainability still exist, the results have been strong enough to change how the world views land restoration. In 2011, the United Nations officially recognized Kubuchi as a global model for land rehabilitation. By 2019, the region was selected as an international demonstration center for anti-desertification solutions. Since then, Wang's methods have started spreading to regions struggling with severe dryness and land degradation, including parts of Africa, the Middle East, and Europe. One of the most notable examples is Andalusia in Spain, the largest semi-arid area in Europe. There, local authorities have begun testing their own Kubuchi-style approach, featuring Mediterranean green walls, native plant restoration, regenerative agriculture, and solar farms integrated with agricultural production. Kubuchi reminds us that even places once thought dead can come back to life when people are brave enough to push past their limits. It's not just a story of sand turning green. It's proof that the future of our planet isn't shaped by circumstance, but by those willing to act. When humans and nature find their rhythm again, the impossible becomes possible. If you want to explore more stories of restoration and remarkable engineering, don't forget to follow Mandarin Tech.